Welcome to Programming in Modern C++. We are going to discuss tutorial 10, how to optimize C++ programs using Rvalue and Move Semantics. We have during the course of our discussion on Rvalue references, universal references and the move operations, we have seen that this support can significantly reduce the necessity to copy, particularly the temporary objects. In this tutorial, we are going to discuss a number of examples to illustrate which of these optimizations can as it is be done by the compiler, and for which it needs the support from the programmer to suggest to the compiler as to what can be optimized out, that is, what can be treated as a temporary object as an R value. And we will get towards building up a small but complete project of sorting an arbitrary data type containing resources to understand this. So, if we talk about optimizing C++ programs, obviously you know there are several optimizations, and C++ has always produced fast programs. But unfortunately, there is one problem area which slows down many C++ programs, that is creation of temporary objects. C++ to keep its object orientation, to keep its implementation of various semantics, need to regularly create temporary objects and delete them. And when you put those things together, then often you have a lot of temporary objects which are created and deleted. Now, sometimes these objects can be optimized away by the compiler, and that process is known as copy elision. Copy elision is an optimization technique that eliminate the unnecessary copying of objects. Right? Copy elision primarily depends on the identification of R values by the compiler, because you know that R values can be removed, can be optimized away once they are used, because since they do not have a name, they cannot be used by the programmer, and therefore, after their use, if they are removed, then it does not really impact the correctness of the program. In addition, what the compiler can do is, in addition to what the compiler can do, we can also help the compiler by explicitly marking R values. And how do we do that? We can do that by providing R value references, or by providing move operations along with the copy operations if they are at all needed. So, in this tutorial, we are going to elucidate some of these scenarios of copy elision and the sorting project that I just mentioned. So, let us first look at copy elision. As I told, it is a compiler optimization technique that eliminates unnecessary copying of objects, and there are several such which exist, the most common being the return value optimization. I have talked about this earlier, but in this tutorial I am going to talk about it in little bit longer length. The other place where copy elision can be used effectively is copy initialization. It is usually equivalent to a direct initialization in terms of performance, but semantically it may be different, because it requires an accessible copy constructor. Right. So, let us see what all can be done in terms of copy elision. So, first let us look at copy initialization of objects. I have a very small class C. Here most often I have written classes as struct, because the issue of encapsulation or access restriction is not the focus to discuss. Whatever we are discussing in terms of structs will apply equally well for the classes altogether. So, we have an explicit constructor which is a parametric constructor, and it has a copy constructor which does nothing, but there is a global variable n which the copy constructor is supposed to increment, right. And we do not, though we have a parametric constructor, we do not have any data member, because we are not interested in looking at the data member values and so on immediately, right. So, in the context of this, we have written these two object initialization. You can easily make out that this is a direct initialization, where we are expected to invoke the parametric constructor, and C1 after that invocation will become an L value. The next one, as you will identify, is a copy initialization. C77, this particular object will be constructed by the parametric constructor, and then from that a copy initialization will happen to C2, and this is, it is to be noted that C77 is an R value here. Right. The interesting thing is, if you actually execute this program and to test whether the copy initialization is, or the copy constructor is getting invoked, or how many times it is getting invoked, we are incrementing n every time it is invoked, and we at the end we print n. Now, if you execute this program, irrespective of whether you do that in GCC or in Microsoft Visual C++, whether you do it in release build or in debug build, whatever, it will always print 0. And you will get amazed, because you know, it is not only that it is keeping the copy construction, but the copy construction has a side effect, it is keeping that as well. And before you think that this is an error of the compiler, let me tell you that this actually is a language specification. Now, you might think, okay, it is not doing something because the copy constructor does not do anything meaningful. So, let us try to put something meaningful in that. Let us introduce a data member, let us initialize the data member in the parametric constructor, print the value of the data member. Also, let us copy the appropriate data member value in the copy constructor, and print its value with one increment. This increment will tell us that this is getting printed from the copy constructor. Right? Then we have a destructor where also I am printing the value, so that we can trace exactly what is happening. Now, if you do that, this is the parameterized constructor. This prints 42 as you expect. Here first C72 is expected to be executed. So, that will call the parametric constructor. So, it will print 72. After that, you would have expected a copy to happen, but that copy call does not happen. There is no printing of 78 happening from here. So, again, even though there is a direct data member to initialize and things to do, those get skipped by the constructor. That is the copy constructor does not happen, and n therefore prints as 0. Right? In fact, if you comment the copy constructor, and of course, if you will say that if I comment the copy constructor, then also how do I know that copy constructor is actually invoked or not, because the compiler will give me a free copy constructor. So, you can comment out the copy constructor and explicitly delete it. You have already learned how to delete a function in a class, explicitly delete that. So, no free copy constructor is provided. Then the C++ compiler will give an error, the use of deleted function. I mean, isn't it a little funny, because if I provide it, it does not invoke it, but if I say that it is not there, then it does complain, right. So, that is what I was saying, that here the behavior is like the direct initialization, which is very similar to the copy behavior, but semantically it is different, because it still wants that a copy constructor must be accessible, right. So, it has to be accessible, then it does not use it. And now, in all this, if you have to understand why this is happening, you have to note that the C77 is an R value, right, because it is a temporary object which you have no control to hold on. Understanding that, let us see that if we now change this code slightly to construct an object from an L value, right, from an L value. So, these remain same, all that this is same, but I add a third initialization for a instance C3 from C1, where you can see C1 is an L value, whereas this one is an R value. Now, you see something interesting, it does as before, this also does as before, but as you try to construct C3 from C1, which is an L value, it actually invokes the copy constructor. And as it invokes the copy constructor, C1 has a member value 42. So, it increments it to 43. So, it prints 43, and at the end of the program you will now see 3 objects getting deleted with their respective values, destructed with their respective values, right. So, this is the basic copy elision that the compiler does. If you want to see that well, if the compiler were not eliding the copies, then how it will look like. In GCC you have a nice way, you have a flag by this minus f means flag, no elide constructors, then it will disable the copy elision, and you can see exactly as you had expected it to see. So, this will invoke the parametric constructor, this will then invoke again the parametric constructor, then it will invoke the copy constructor, you get 78, and after having invoked that, the L value C77, the temporary object which was created, has no use for any further. So, that temporary object is now deleted right here, and then this is the copy construction that you have seen earlier. So, you are left with, you have created 4 objects and you have deleted 1. So, you are left with 3 objects that are deleted at the end. You will be able to see that the value of n is 2, because you have invoked the copy constructor twice, once here and once here, right. So, in copy elision, basically what you are doing when you do not have this flag on, what you are doing is, when this object is constructed as an R value, a temporary object, you do not actually copy it to C2. Rather, what the compiler does for elision is, compiler takes the address of or the location of C2 and constructs the temporary object directly there. So, though it is a temporary object, it is not constructing and then copying it, but it is directly constructing it right here, which is actually semantically correct. Now, that justifies why this call is not made, right? And why does it still need the copy constructor definition? Because it needs to know whether it is allowed to make such a copy. Though it is constructing this temporary itself in the location of C2, semantically it is a copy operation. So, it wants to know whether that copy operation is allowed, but it is optimizing by directly doing that construction. That is the reason it does not need to call this particular copy constructor. So, that is the kind of copy elision optimization that happens. Let us take another example of copy elision, which is return value optimization. We have the same class. I define 2 functions f and g. F constructs an object by parametric constructor and directly returns in by value, and here it constructs into a temporary into a local object, and then returns that by value. In both cases, he will expect that there will be a copy construction, there will be a direct construction by the parametric constructor and a copy constructor by return by value. Try to invoke these two functions, you will find that there is just the direct construction happening, no copies are being made, which you can argue that both of these are actually R values, and the compiler sees that this R value has no use. It has not been assigned to anything or passed to some other function or anything. So, it deduces that it is enough to just construct the object, but it then does not need to actually copy it, it has no further use. So, that temporary object can be deleted, right. So, that is exactly what. Now, let us just give it a little twist, give the same, this is same, except that now instead of just invoking the function, I am invoking the function to initialize two objects C 1 and C 2. You will see the same behavior, 19 constructed. So, this is constructed, but the copy constructor is not invoked. Why is the copy constructor not invoked? Because it does that copy elision. That is, it constructs this Ci, which is local to function f, in the address of C 1 itself. So, that it does not unnecessarily need to do the copy and then delete the temporary object. It saves on both of that. Similarly, when you do G 35, you have constructed C. So, you get 35, and this return by value of this variable C is again optimized out by doing an elision. That is, the compiler goes to the extent to see that this C will actually get copies to C 2. So, when it is constructing this Ci, it is constructing in the address value of C 2 itself, right. Of course, now since both of these have actually been instantiated into two local variables of main, their deletions will happen at the end, right. You can again use this you can again use this flag to force that the compiler does not do any such copy elision. If you do that, then in this case it will first construct this object, then it will copy, then it will delete the temporary object, and then it will again copy into C 1. You can see that 2 copies and 1 deletion is happening additionally here. Whereas, when you do the other thing, you see the same behavior. It first constructs, then it copies, return by value, then it destructs the local object C, and then it copies into C 2. Right. Finally, C 1 and C 2 are destructed. Right. So, you can see that copy elision, I mean how much of effort the additional task which is unnecessary can be actually handled by the copy elision optimization. So, these are not just optimizations by the compiler, but they are language specified also. For example, in C++ 03 itself, you had this kind of optimizations given that if you do return t construction by value, then only one call to the default constructor will happen, exactly as we have seen. Similarly, there are in a return statement, if your operand is a named object, that is an L value, then you will have NRVO, named return value optimization. If it is initialization of a object with a nameless temporary, that an R value, you will have a R value optimization. And in C++ 17, this R value optimization is no more considered a copy elision. It is mandatory and it is a different or optimization altogether, right. But C++ 17 we are not discussing at that length. Okay. So, having said that, now we are set to just show you a sample sorting project where you can see this benefit. So, we have a resource class R. So, it is just a dummy resource class which will just have an integer, a data class which has a resource of the resource class R, and we have templatized swap function, a bubble sort function templatized to sort an array, and a main function to give the calls. So, let us see how does that work. So, first we start with functions with copy, classes with copy support, everything is with copy support. So, this is my resource class, it has constructors and destructors as expected, and my data class has a resource of that resource class R. So, it holds a pointer to that resource. So, every time it has to get a proper resource object constructed to get this value. So, in the data class it has a pointer to this. So, it has all its usual operations of default will set it to null, otherwise if it is parameterized then it will construct an object with value R I, will allocate for that and put that pointer. In case of a copy construction, it will copy the value of the resource from D, the source object, and construct a new object. So, that is a deep copy will get done. This is exactly what happens in the copy assignment operator. Delete will have to release this resource. So, the standard scenario, and then we have a friend operator outstream function to just do our understanding of what is going on, and I have provided a operator greater than comparison operator of two D objects, so that I can do sorting based on that. Right. So, now to do the sort function, what do we need? This is the bubble sort function. It assumes that the data values are of type T, and rest of it is bubble sort function, which is which you know. So, I will not going to explain. The reason I have chosen bubble sort is it is easy for analysis, and I am going to construct a worst case for bubble sort, that is elements are sorted in a certain order and I want to sort them in the opposite order. So, this is the comparison which will use the comparison operator. Actually, I should write here not D, I should write here T, T colon colon operator greater than, and that will need to swap two objects. Now, when I want to swap these two objects, then naturally I make use of this swap function, which is a standard templatized swap function, which as you know does multiple 3 copies. So, 3 constructors and destructors of the resource object with copy will have to be done, right. With move, the scenario will change. Now, let us see what happens in the main function. I declare an array. This is the number of elements, size of the array and the number of elements, I assume them to be same. I declare an array, which means that the default constructor of the D class is used to fill the array with D objects having null resource pointers. Then I fill up this array using with D n minus I objects. So, you can see that I am actually filling them up in the increasing order, in the decreasing order, right. So, 10, 1. So, this is the order in which the array will be filled up, because I said I want to create a worst case, right. So, every time I do this, I will construct this D n I by the parameterized constructor. Then I will have to do the assignment using the copy constructor to construct and deconstruct the R objects as they exist. Right? This is just to print the array, so that I can see what is in. Then I call the sort function, the templatized sort function, and call the sort output. Now, and the sort, what does the sort function do? It tries to sort them in the increasing order, but this is strictly in the decreasing order, and I want to make them into increasing order, right. So, I want to do just the opposite. So, which means that if I go back to the sort function, it will be easier to see. Yeah, if you look into this sort function, then you will see that since it is strictly in the decreasing order, and I want to maybe, so every time I do this comparison, this is going to succeed, right. That is the reason I am using bubble sort. So, very easy worst case. So, since the numbers are decreasing and I want them increasing. So, every time I compare the consecutive pairs, they are in the wrong order. So, this will always be true, which means that as many times as these loops go on, this swap function will be called, right. So, if I put a little algorithm analysis into this, then this basically means that in every loop it will depend on the value of I, how many times it happens, and it goes from 1 to n minus 1. Hence, the total the number of times the swapping will be done is n into n minus 1 by 2. So, in every swap I have three assignments, copy assignments. So, what will happen is I will have 3 resource objects created and 3 resource object destructed, right. So, this is the amount of construction destruction of the resource objects that I am going to do. Now, this was analytical. So, if I really want to see the number that is happening, I need to provide some support for the statistics, right. So, that you can these are techniques you can do in any class too, if you are working on the performance. So, I put some counters, a counter to count the number of times direct constructor is used, number of times the copy constructor is used, and the number of times the destructor is used, and the respective counters are incremented in the respective function calls. And then I have a stat function, which basically prints the values of these counters at any point of time. All of these are static because they are not bound to any particular R object, but should be usable anywhere. Now, since I have these static members, so I will need to instantiate them in the global space, and I instantiate and initialize them with 0. In addition, I do something interesting is I define another class struct, in whose constructor I call this stat function, say with program start, and the stat function again in the destructor with program end, and define a variable of instantiate it in the global. So, what will happen? This is a static object, extreme stat will become a static object. Therefore, as you know, static objects must be constructed before main starts and they are destructed after main ends. So, this function will get called before main starts and this function will get called after main returns. So, I will be able to get the first and the final statistics. So, that is just a nice technique to create statistics. So, I do the same thing in the main. After the default initialization, I print statistics. After filling the array, I print statistics. After sorting, I print statistics, and I get all of these. So, if you just recall, what will this mean? This will mean that initially everything is 0, because no objects are created so far. Then after the default, again no R objects are created because the D objects initialize the resource as null pointer. Then after I initialize the array by this, every time I construct a D object with parameter, an R object will get initialized, will get created. So, I have 10 creations of these, and then they will be copied 10 times to ARR. So, there are 10 copies and those temporaries will be deleted. So, there are 10 deletions, right. So, if you look into that, and then I have this, then I have the sort, and in sort you can see that creation still remains to be 10, but I have 145 copies created instead of 10. So, 135 more copies have been created, these are because of the swap, right, and those are created and destroyed. So, just see how wasteful it is. And if you tally it with the analytical formula we have just derived, you will find that this is 135, which tallies with the fact that 10 plus 135 is 145. Right. Then you have the array, and finally, you have the total copies created are 145, direct creation is 10 from here, and therefore, the 10 objects in the array that existed when the main ends, those will get destructed. So, you will have 155 destruction. So, you can see that you actually needed 10 objects to be created and 10 objects to be destructed, but you have along with that you have created 145 objects additionally, R objects additionally, and 145 R objects you have destructed. So, that is the basic problem with temporaries. So, how do you get rid of this? You know that you can give a move support. So, you say I will not copy, if not required, I will not copy the D objects, I will move them. So, I have a move constructor and a move assignment operator added now. So, how will that impact? It will impact in the sense that if I run the program again, when I am doing ARR I assigned d n I, d n minus I is a constructed object and d n minus I is an R value. So, in this assignment, it is not the copy assignment which will bind, it is a move assignment that will bind. And in the move assignment, I will simply move the resource, I do not need to copy the resource. So, after 10, when I do this, I will have only 135 copies made instead of I was earlier having 145. I will have 135 only, because these 10 copies that were required here, copies and destruction that were required here is saved. So, some benefit has been obtained. Now, next we can actually, the culprit is a swap function. So, what I can do is I can use std move from the library in the swap function and make all of that move. So, that the values just keep rotating around, they are not copy created. So, if we do that, then naturally all of these will be the first one, the second one, the third one, all are move assignments, right, move of values. So, for that no R object needs to be created or destroyed. Therefore, if you with this modified swap function if you run, you will see that in the sort there is no copy created of the R object, neither therefore, they are destroyed. So, if you analyze, all that you need is 45 swaps, which needed earlier 135 construction destruction, but all those unnecessary construction destruction has been optimized out. Now, at the end you have just 10 constructions for the 10 objects and 10 destructions for the 10 objects. The resources are optimally used. So, that is the direct demonstration of the benefit of what you get by providing the move support. Here I have given a table for your understanding that there are two places to support this in this particular project. One is in the class D, you can have only copy support or copy and move support, and in the swap function you have only copy version of swap function or move version, and naturally 4 combinations. So, if you do say if you do not have a copy move support in D, then irrespective of which swap function you use, you have the same complexity. If you have move support in D, but not in the swap, you get little less, but you still have a lot of unnecessary copies happening, whereas if you are move support in both, then you have no extra copies being done. So, order n square copies are now really optimized out, right. So, that is a big optimization that the programmer can guide to. Guide the compiler to do, and this is just one example I have shown. You can say this in the whole. In the next couple of slides, I will not go through. I have just put together the entire code one after the other as it finally stands out. The struct R, the struct stat, the struct D, the two versions of the swap function, the sort function, and finally the main function. So, you can put them together into one source file and execute with move, without move, and so on, and experiment further. And here are some problems that you can try out, like providing construction, destruction, counting, and statistic generation support for the class D objects also. We have just done for class R, the resource object. You can change the resource from being a pointer resource to an actual data member resource, and you will need to make changes in the class R as well to optimize unnecessary copies out. You can explore on the move support, which are available in containers in the standard library, particularly vector and map, and so on. So, in this tutorial we have tried to explain the optimization by copy elision, and we have understood the copy and move optimization by Rvalue and Move Semantics through a small example with a complete project. Thank you very much. I hope this will be useful for you in understanding the Rvalue and Move Semantics and one of their use in this context. So, see you in the next discussion.